Alrighty, let's get this started. I hopefully won't pick up my dogs that are running around at my feet. They have a tiny little squeaky with the squeaker punctured, so you might just hear a very soft, like squeaking sound of a toy in the background. Hopefully, that could get drowned out. Also, hopefully, my voice is coming across alright. It's about 30 past midnight, so I'm trying not to speak too loudly. We've started grading your Lab 4 paper, so I expect the grades hopefully to be out all finished grading by next Tuesday. And I will also be hosting office hours the Monday before the report is due, since I know a lot of people like to wait till the last minute to do those reports. So, also, I apologize for not getting this video out earlier. Just as proof, I had a massive presentation to do for my end of the semester classes, so hence why I haven't devoted so much time into making this video, but hopefully now we can get that all out of the way and actually focus on the lab itself. So, we are looking at energy losses in flow through pipes. So essentially, you saw in lab, you had this device where water just went in through the top, out through the bottom. There's some pipe. You measure the pressure drop before and after some section using manometers or a digital pressure gauge, right? So essentially, how do we go about interpreting this data? Like, what does this mean? Well, if you guys remember the Bernoulli's equation, right, you'll notice on the left-hand side it's like P1 plus 1 half rho V squared. You might have a potential term. And then if you remember in lab 3, right, you find out that the Bernoulli equation doesn't hold. You had some deviation from theory. And that's because we never calculated frictional losses. Well, in this one, we're actually calculating those frictional losses, right? So, just to make the video a little bit quicker, I'm not going to go into too far of the derivations. Just understand that you have something called your friction factor F, and it is related to the pressure loss here in terms of delta P over this denominator, right? So this is kind of like your velocity term as well as your distance. This is like a significant length over distance, so it's some kind of metric involving the geometry of your pipe. Something of note, and I'll show this later, when you're looking at your manometers for the turbulent regime, they just give you the straight delta P, right? You don't have to do this 2GH, where this H here, that corresponds to the manometer height difference, right? It's not the length of which the tubes move across, okay? This is the manometer height difference, okay? You will only see this for the laminar section, and this is the turbulent section, all right? So what do I mean by laminar or turbulent? You guys have seen in the lab when the water came out of the apparatus, it seemed very smooth, quote unquote. You know, you could take a video of it and it looks like the water's not really moving out of the pipe because it's that smooth. And then when it gets to the turbulent regime, you know, you can kind of see that the water doesn't look crystal clear and smooth, right? This typically happens. The laminar regime for a smooth pipe is less than 2300, and then anything greater than 4000, you see that your Reynolds number is considered turbulent, right? And then in between, you have this weird region where sometimes the flow is laminar, sometimes it's turbulent. If I remember correctly from the data, we don't really deal in the transition regime, but you know, something to look out for. Also, sorry, hopefully my coughs aren't coming too hard across the mic. Allergies are hitting pretty bad right now. So, anyways, so let's look at this. This is called a Moody chart. Moody chart is basically a you could relate it to your your drag coefficients from lab 4, right? So you have your Reynolds number, which takes into account what kind of fluid you're using with the rho and mu, how fast your characteristic speed is of the water moving through the pipe, or fluid moving through the pipe, and then the diameter of the pipe. And your friction factor is essentially kind of like that drag coefficient, right? So this gets involved in calculating the total head loss, or predicting the total head loss, as just fluid moves through long sections of piping, okay? So you can see here, this line corresponds to 64 divided by Reynolds number. And then you have right here, this is, I think it was Blasius, who studied a lot of pipes, or water moving through smooth pipes. And if I remember correctly, this is 0.316 times the Reynolds number raised to the power of minus 0.25. And you'll be comparing your experimental data to see if it lies within this regime. Now notice how this says smooth. Realistically, if you use, PVC pipe, copper, steel, basically anything, it will have some kind of microscopic roughness, right? Like the water molecules will interact with the different divots, crevices, and structures of the pipe itself. So essentially, I think you guys have a homework question where it talks about commercial steel. And commercial steel, if I remember off the top of my head, has a absolute roughness of like 0.000015, and then you can relate it to like a 1 centimeter diameter pipe. So basically, if you know your Reynolds number, the speed of which your fluid's moving through it, you know your relative roughness, you essentially can move through and like connect the dots. So I think I have it pulled up here. So let's say it's 60,000 or 600,000. So you can connect the dots to something that lies along like this curve right here. So then you can move across and estimate your frictional factor will be about 0.01567, so about 0.018. Very rough designs, but sorry, best I can do right now. Something you guys should really pay attention to is that this is a log plot. So if you'll notice here, the graduations here is 0, 1, 2, 3, and so on. Looks like these are kind of numbered a little funny, but essentially understand that these aren't equally spaced, right? Just the way that logarithms work, you have to kind of understand how to read the graduations of all of these. And we'll have some examples later, but I just wanted to show generally what the Moody chart looks like and how you interpret log plots, okay? So speaking of which, let's kind of go over what you collected in lab. So you remember this table, where really the only things that you would have collected were the total volume, the time of which it took to collect, however, how much volume you had. So for example, I think the graduated cylinders you had was about 100 milliliters. I saw some people collecting 200 milliliters. Make sure you convert that properly. Then you had like manometer heights for the laminar sections. For the turbulent sections, you just read off kPa or psi off your manometer, so be sure to convert those to kPa. And then essentially these 4 columns are all you had to collect in lab. The rest can be found through number crunching, right? So let's see what those number crunchings look like. So this was the data given to me by one of the students in your labs. So he found the volumes in milliliters, converted it to liters, then he converted it to meters cubed, and then he recorded the times of which to take those volume measurements, and your manometer readings right here. And the biggest thing that you want is this delta H. Q is just your volume divided by the time that it took. We've done this many times over. Your area, your mean velocity is just Q divided by your area. Okay. And your area is, just in case you forgot, it would be pi times the diameter squared divided by 4. Which, by the way, if you ever wanted to write out an equation in Excel without it auto-formatting saying, oh wait, no, you're actually trying to do a real equation, if you put an apostrophe there, you can now just type out your equation. See? So it won't solve it for you. If you don't put that apostrophe there, it'll actually try solving the equation. Just something to note. Anyways, so you have your velocity, your experimental friction factor for the laminar setup is right here. Okay, so this is how you find F, where H, or rather this should be delta H. Okay. This is how you find your friction factor. D, I think, is given in the lab manual as 3 millimeters or 0.003 meters. And the length is given as 0.5 meters. Okay, so that's pretty nice. Your Reynolds number. Okay, this is something I saw a lot of confusion about. So normally your Reynolds number is given as rho times V times D divided by mu. But in your lab manual, it gives you the values of nu, not mu, but nu, right? Nu is the kinematic viscosity of water. Mu is the dynamic viscosity of water. And when you divide the dynamic viscosity of the water by rho, you're essentially normalizing the dynamic viscosity. You get your kinematic viscosity. Okay, so that's where they get this equation from. And then V is essentially just found using the flow rate equation, just rearranged, right? So your final Reynolds number should be something like, doing quick math inside my head, definitely not stalling for time, should be pi nu d, I believe. Right? Cool. I might have made an error. Maybe not. Just kidding, I did not. Okay, cool. Yeah, so this would be how you find your Reynolds number. Okay? So, something I'm already noticing here is our Reynolds number. So it's about 1,000, 2,000. If we look at our Moody chart, where is it? Here it is. 1,000 to 2,000, we're kind of getting dangerously close into this transition regime, right? We'd prefer to be slower in the laminar flow, but understand you still can have laminar flow inside the transition regime, but you might have something that trips it into being turbulent. So maybe there's a very small nick in the pipe, and suddenly it goes from laminar to turbulent, right? So that's essentially the regime that we're in. And my dog just found a squeaky. If he brings that into the office, I will remove it. Apologies if it comes across the mic. Okay, now we're good. Okay. So your theoretical friction, theoretical friction factor is simply 64 divided by the Reynolds number. Okay, so I'm going to show you later how to data process this, but essentially you need to have a column here that is just 64 divided by the Reynolds number. Okay, now this grade region right here, will be used later in another way to look at your data. I'll cover this soon, but just understand you should have a column. I recommend it. You have a column. You will have to do this, by the way, for the turbulent flow, but have a column that is the natural log, ln, of the Reynolds number, your experimental friction, and your theoretical friction. Okay? Your turbulent flow, looking over here, you'll now see that your manometers will give you PSI measurements. So you have a high and low. It's okay if you have your P1, P2 mixed up, doesn't matter. The main thing that you only care about is the pressure differences, right? So mind you, the manometers gave you PSI. You're gonna have to convert it to kilopascals, which then later when you do calculations, you're going to want to convert kilopascals into regular pascals. So if I look at my friction factor, you see that I have converted from kilopascals to regular pascals by 1,000. Okay. So our Reynolds number here is about 8,000 to 40,000. And once again, if we're looking, so 8,000 to about 40,000, we're in this region right here. Okay. So it's kind of going from this transition region into what we would consider turbulent, right? Okay. So yeah, once again, we have more columns for the natural log of friction factor, Reynolds number, and then our theoretical friction factor. So why am I taking the natural log of things? Well, that's a good question. So let me take a step back and tell you how to use natural logs. Okay, so anytime something is written as a natural log and it is a product of something, so you take the natural log of this product, you can split it apart into an addition of natural logs. So here it's natural log of k plus the natural log of b. For logarithms of exponents, so here we have the natural log of c to the power of n. The n just gets taken out in front of the natural log of c. So then if we're looking at this original equation, if we let b be c to the power of n, we can see through number crunching that the product becomes the natural log of k plus n times the natural log of c. So why am I teaching you this extra math outside of maybe to do a really dorky party trick? Well, if you remember, F, your theoretical friction factor, is related to 64 divided by a Reynolds number. Another way to write this is 64 times the Reynolds number raised to the -1. So this is a power relationship. So in general, if you were to use a power trend line, the equation that it would give you would be something of y is equal to a, so sometimes some kind of constant, times x to the power of k. Okay. Another way you can look at this, so if you were to use this, you'll see this in your log plots, but you can manipulate your data such that if you take the natural log of both sides, you'll get natural log of f as your plotted y values. You'll have k times the natural log of your Reynolds number plus the natural log of a, where a here is 64. Okay. By the way, the natural log of 64 is this value. Why am I doing this? Essentially, it's just another way you can look at data. Honestly, if you're comfortable using power trend lines and understand how power relationships work, not power dynamics, but power relationships, you can just kind of comfortably use power trend lines. But this lab kind of wants you, or is kind of forcing you to look at your data in different ways that might be more palatable to others. Okay. So if we look in the turbulent regime, this is our general equations for turbulence. Take the natural log of both sides. You find that you'll have some constant times the natural log of Reynolds number plus some constant k, right? And then ideally, Blausius said n should be minus 0.25, and then k should be 0.316, right? Why do we split it up like this? I forgot to mention this. If you split it up in this natural log form, you can use then a linear trend line after you do this transformation, so you'll make a separate graph. Or then you can use a linear trend line where it's just y equals the slope times x plus b, okay? So ideally, it should look like for your laminar, this is your equation. It should look like your trend line should look like y is equal to minus 1 times x plus 4.1589. Again, this value comes from a being 64. Okay. And then again, if you look over here, the linear trend line should look something basically like that. All right. So let's look at the. That's great. So let's look at the ways that we look at our data. So all I did was I just essentially moved my data points to a table down here. I think I also rearranged it such that I had increasing Reynolds number. You don't have to do that. I just did that just to make everything line up correctly. And also, you don't have to do this part where see how it's grayed here. I only added those because I just wanted my theoretical trend line to be continuous and kind of go off the graph, so I can play with the max min values and not have to worry about seeing the entire trend line. Okay. You can see here though, I have my experimental f, my Reynolds number, my theoretical f, and then I have your natural log of Reynolds number, natural log of experimental f, and then the natural log of theoretical f. So, what are the two ways of plotting this? Here is the log-log plot. If you don't try to use the log-log plot, I'll show you what that looks like. You'll get something that looks like this. Something that is basically useless, right? You can't really see much detail. So what you do is double click the x-axis numbers and you'll click right here, logarithmic scale. Okay. And then again, for the y-axis, logarithmic scale. And now you can see that when we do the logarithmic scale, if it is a power relationship, so that is y is equal to some constant times x raised to some power, it'll look linear, where the slope of this line will be the exponent, right? Apologies. So we can see here, I have plotted power trend lines. So let's pretend you don't know how to do that. What you're going to do is go over here to add chart elements, go to trend line. For now, just click linear. We're going to change it. Select experimental. And you can see it when I try doing a linear trend line, it doesn't really connect the points that well. And in fact, if I hit display equation on chart, you need to do this section. And then display r squared values. You'll see my r squared value isn't terrible, but it could be better. So if I double click this trend line, or if you don't double click the trend line, you can go up here and then go series experimental trend line 1. That'll allow you to do your different formatting. Click power, and now we can see our trend line fits a lot better. And then I also did a power trend line for the theoretical, just to show what it would look like. So here's my theoretical. If I try doing linear, again, look how awful that trend line fit. It does, you can't even see it. It's just that awful. So if I do a power, it should fit perfectly, where the power trend line will give me that constant out in front, and then the exponent of the power of which x is raised. Okay. Now, let's say you wanted to make things look a bit more linear. You didn't want to do a log-log plot. So I'm going to take the natural log of my x data and the natural log of my y data. So x data being the Reynolds number, y data being the friction factor. And it'll look something like this. Okay, so for instance, let me try showing you what happens if you have your trend line be well, yeah, actually you can't show the power because it goes through the x-axis, and essentially if you have any values that lie at 0, it won't let you. But now you can see, anyways, my theoretical trend line is y is equal to minus x plus some constant, where once again that constant is just the natural log of 64. That's where this value comes from. And this is just a rearrangement of y is equal to 64 divided by x, right? This is essentially what we're trying to find. And if you take the natural log of both sides, you'll find minus 1 times x plus the natural log of 64. So you can see that these are identical. You can see here the experimental trend line, the linear trend line. Once again, this is your power that is related. And then this is that coefficient out front, right? So if you're trying to interpret this, if you're trying to reconstruct what your original equation looks like, it would look something like this. So F experimental is equal to 1.9166 times x raised to the power of minus 0.6588. Or, well, where x should be written as your Reynolds number. Okay. This is not a simple concept. Many of you, this might be the first time you are seeing this. So just give it a few seconds, see if you can replicate what I got, see if you can make heads or tails of it. But regardless, whether or not you go with the log-log method or the natural log linear method, you should be able to find the coefficient that's out in front and then the exponent to which the Reynolds number works at. So you can see here I have reconstructed both in the same way. Okay. Now, if we look at the lab manual, it doesn't explicitly tell you need to do that for the laminar flow. Right? Theoretical value for laminar flow knows that a relationship of this type becomes a straight line when plotted on a log-log plot. Okay. So it doesn't tell you that you need to solve this, take the natural log of both sides. Okay. The turbulent flow, however, does. So again, let's look at the turbulent flow. Let me zoom out a little bit. So the bottom row here is my turbulent values. Once again, I might have rearranged it just where I have increasing Reynolds number. I put these rows up top just to overextend my theoretical trend lines just so I could see everything. Okay. And I also have my power trend line, both theoretical and then my experimental values. Okay, and you can see here I can very easily, using the power trend line, find my coefficient and the exponent. All right, but that is not the only way you can do that. In fact, compare these. Okay, so it seems like you don't have to take the natural log, though I thought I saw it. Oh wait, no, it's up here. You want to have the plots of the natural log of your friction factor versus the natural log of your Reynolds number. Ignore this. Ignore the natural log of the manometer versus natural log of velocity. I don't think it's very useful for your guys' understanding, and I think it might just kind of confuse many of you. And that's not a dig at you guys. It's just hard to kind of see the relationship of this without doing additional math. So for now, just focus on this, okay? So, this is the plot of which you have. You can see that we have some kind of relationship. If you take the natural log of Reynolds number, natural log of friction factor, you can see once again, you can reconstruct and find those coefficient values and power values. You just have to do a little bit extra math. But we actually have a very good power relationship here for our experimental values. I think for another student, I tried doing some calculations, and their values weren't the greatest. That might not be their fault. It could just be that when they were trying to record data, either they weren't eye level with their graduated cylinder, so trying to have accurate timestamps might have not worked as well. Could also been that their manometers were not zeroed properly. Could be a lot of factors, but just make sure you please don't just say human error, okay? Say there was an error in recording because of X or Y, or maybe the transducers were failing, something like that. I don't know. But please don't say human error, okay? Usually when you say human error, that implies that you were not competent enough to do the experiment properly. So that's why we typically say, never say human error, right? But once again, you can either do the power trend line or the linear trend line using the natural log datas. But you should be able to get the coefficient values regardless and the exponent values regardless. If you do the natural log linear relationship, just know it takes a little bit extra math just to get that coefficient, okay? So I thought this would be kind of helpful to see where these points lie. You do not have to do this part. I just did it because I always find it interesting. So for our particular experiment, we can see where our data points lie. So it's just above the laminar flow regime. If this was truly laminar with a smooth pipe, our point should lie on this. You can see it lies a little bit off this line. Now this could be things from not being eye level with your graduated cylinder. Could be that there's actually unaccounted for surface roughness that would make us deviate from this line. Sorry. And these values right here, I think these are pink. Maybe they're gray. I don't know, whatever colors these are. These are our turbulent values. So, to me, I would have predicted that they would have lied above in this region where it's partially laminar, partially turbulent, but now it's accounting for the surface roughness. But with this particular data set, I could see that they fell below. So it might be in this transition region where it's partially laminar. I know the other data set from the other students, they found theirs to be above the theoretical line. So it would be where you'd account for that kind of turbulence. So again, I'm not going to lambast you for not having something that's lying perfectly on the line, or it's perfectly up here, or things like that. I just want you to tell me basically why. Why do you think that's happening? And once again, please, I am begging you, do not say human error. But that basically wraps up the data analysis for this lab. Compared to lab 3, really any kind of data analysis will be easier, but there's not too much data analysis you have to do. There's only 2 questions, right? There's no additional questions you have to answer. The only thing that you should do is just have the natural log of friction factor versus the natural log of Reynolds number, where this is on the x-axis, this is on the y-axis, and then answer these. Okay, that's basically it. The best way to do this, to compare those values, if you look here, once again, all I did was I just looked at whatever the coefficient was and the exponent it was raised to, and then I just compared it. So ideally, this is supposed to be 64, this is supposed to be -1 for laminar. For turbulent, you can see here, it's supposed to be, A is supposed to be 0.316, and N is supposed to be -0.25. This one's actually pretty close. So, that's satisfactory enough, and maybe give an explanation of why. But that's all I have for you. You guys have been absolute pleasure, this lab. And if you see me around campus, be sure to say hi, let me know how things are going, and I'll see you guys later. All right, see you guys.